I will try to take the advantage of viewing the complex functions and gradually introduce the standard form of the root locus, and show how can we do this one systematically. So, for example, here we consider, say, the two complex numbers. S1 equal to A1 plus JB1 and S2 plus A2 plus JB2. Consider the two numbers, and then we can see, for example, the base of S1 and then the magnitude of S1. So here, for example, here is our complex plane, and that is the real and imaginary. And say, for example, S1 is here. Okay, so by definition, we place the S1 and S2 on the complex plane. Real part is A1, and imaginary part is B1. So from here, the magnitude so this is the magnitude. So basically, you label the distance from the point to the origin, and that, by definition, is the A1 squared plus B1 squared. Okay, and this is called the phase, or sometimes we call whatever the angles, and that one actually is the arctangent of the imaginary part divided by the real part. Okay. So that is the definition for this. And then the second one we talk about is the relative. Difference. For example, S1 minus S2. So again, we on the complex plane, and say we have S1 is here, for example, and then for example S2 is here. So S1 minus S2. S1 minus S2 represent is this new complex number, and then you represent this by arrow. Okay. And so in this way, this is the amplitude. This is the magnitude of S1 minus S2, and many times we use the absolute symbols S1 minus S2 to indicate the magnitude. So for example, here, if you like, you can use this symbol S1 to indicate the magnitude. Okay. So S1 minus S2, they have a magnitude. You simply measure the distance between them in the plane, and this angle here, and is the phase angle of S1 minus S2. Okay, and S1 minus S2 here, if you want to do the calculations, S1 minus S2, and that by definition is the phase angle. Let me write it up here. The phase of A1 minus A2 and plus B1 minus B2. Okay, so here I put up into the real part and imaginary part. So here, by our definition, is B1, the imaginary part, over the real part here. Okay. So here, those are the complex numbers, and we can extend the concept of the magnitude and phase angle to polynomials. So the third one is consider a complex function. And for example, say the complex function is polynomial, say Q over S, Q over P. Okay. So P, Q are certain polynomial functions in S individually. And basically S representing is any complex number. So here is a typical definition of the complex polynomial. So in this way, here the magnitude of LS, and by definition is using these symbols, and the phase of LS, and again by definition we're using these symbols, using the symbol with this one. By doing so, basically I tell you nothing. Okay, I tell you nothing. I only introduce you the symbols for those things. But how to calculate this? And so, for example, here you have to remember this is a complex function. So here S is a complex number. So you simply calculate whatever the value of S and plug into this function. You implement the calculations. Then you do the repeating the whole things here. And furthermore, so for this one, the phase angle basically is the phase angle of the denominator, the numerator, minus the phase angle of the denominators here. Doing so, maybe we can look at a few examples to see how can we do this one. So for example, here the LS equal to 1 S plus 2. So if we have these functions, and then because here the S is a complex number, and say S is any general, say, let me say sigma plus J omega. Okay, so any numbers here, we just do the symbols here. So therefore, so here the LS, we simply plug in that numbers here. So basically that is 1 sigma plus J omega plus 2. And let me rearrange to have the real numbers together, sigma plus 2 plus J omega 1 here. So again, you simply, for whatever the S, the value of the S, you plug into this polynomial, the functions, and do the calculations. And how come today we have a full house? No, never mind, that's a joke. So here, based upon this one, then we simply do the calculation. So the magnitude, here the magnitude, here is again is the magnitude of the denominator divided by the magnitude of the numerator divided by denominator. So here we can put into here. So the magnitude of the numerator divided by the magnitude of the denominators. Okay. So here from individually we can plug into the original definition here. So 1. For example, the magnitude of 1 in this way, again, this is very dummy. So 1 is here. So here the magnitude of the numerator simply is equal to 1. Okay. And for this one, again, we can plug into this equation here. And because we have a real part, we have an imaginary part, we can locate the point. And we simply take the distance between the point. So basically this one is equal to this. Sigma plus 2 square plus omega square. Okay. And the angle the angle, again, we take out this one. That is the phase difference, the difference of phase between the numerator and denominator. So that is the QS. One minus sigma plus 2 plus j omega. Okay.
Why is it
Again, which here?
Never mind.
Okay. So okay, so for this one we'll continue. So what is this? You can see for one is phase angle equal to 0, right? Okay, so that is 0. And this one, what is that? So maybe we can draw this again. Sorry, I will kind of block your way. Thank you. So for this one, we can draw here. So for example, that one has the real part sigma plus 2, has the imaginary part omega, right? So that means here that is the magnitude, and this is the phase angle. Phase angle by definition is arctangent, and the imaginary part over the real part here. Okay, so here for this one, that phase angle simply is minus of that one. Okay, so we can look at another example here. So here that for example, as minus 2 as plus 2. How about as plus 1? So here we can calculate the magnitude here. So that basically is the magnitude as plus 2 and magnitude as plus 1. So, for example, here we say as equal to any numbers, any complex numbers, say, for example, this one. So basically this one is equal to sigma plus 2 plus j omega, sigma plus 1 plus j omega. So that is sigma plus 2 square plus omega square, and sigma plus 1 square.
Is it s minus 2 or s plus 2?
Where?
The numerator.
Numerator?
The
Sigma.
first one.
Oh, never mind. Okay, it doesn't matter.
It does matter.
Yeah, okay. Sorry. And so for phase angle, this is LS, and that is the phase angle of S plus 2, and minus the phase angle S plus 1. Okay. So what is S plus 2? So for example, here is 2, and say here is sigma omega. Okay, so that is the point S plus 2. Here the S plus 2 basically is S minus this one. So here that is meaning is the difference between the two complex numbers here. So here S plus 2 basically here in our complex plane, if you really want to illustrate geometry, and that is this. Again, we take up this one, right? So the difference between any two complex numbers is, by definition, is the S1 minus S2. So here, in our form, we are S plus 2, we put it to that kind of standard form. So that is in this case. Okay, so therefore, the phase angle of this one, actually, you're going to measure is this one here. So to measure this one, basically, is arctangent of this divided by this, right? Okay, so you don't need to memorize any equations. The only thing you need is, in my opinion, is this one. 1 and 2 are the most basic definition. once you have a definition, you simply work together with the trigonometry, in particular arctangent or tangent, and that's it. And all the functions, you simply plug in the value of s into that polynomial, you simply do the calculation, and that will be work. Okay, so back to here. So for this one, we can see arctangent, this one will be equal to arctangent. So we simply work on this one here, and what is this? This is omega, right? And what is this? This is sigma plus 2. And that is work out from the geometry, but some people like to memorize, okay, the phase angle is arctangent of the real part over the imaginary part. The imaginary part over real part. Okay. So some people like to memorize, but it's not necessary. Okay, everything is told by this kind of geometry here. So in a similar way, this one will be equal to arctangent, and the real part omega, and sigma plus 1. So maybe in between, I need to add one more line to express the real part and imaginary part. So here, if you like, you can add one more line. Is here s plug into here. So this one will be as sigma plus 2 plus j omega and minus s plus 1 plus j omega. Okay. So if you like to memorize the equation phase angle equal to arctangent of imaginary over real parts, then you simply add one more line, and from here you can tell which value is imaginary omega, and in the real part is sigma plus 2. Otherwise, you simply on the side, you simply draw a simple graph, and you can tell it. Okay. And another example, more complicated, is this. So say if we have these functions, Ls will be equal to 1 plus k qs ds. Okay, equal to 0. So now you can see this is the standard form. This is standard form of our root locus. But don't worry, here you simply look at this one as the complex function. So for this one, and we want to determine is how can we do this? How can we apply the complex function techniques for this one? Basically, here where k is parameters is a non-negative parameters, and this is the standard form of the standard form for drawing the root loci. So in this way, we have this, and k is a certain constant. So simply we rewrite the whole thing. So q over p equal to minus 1 over k. Okay? So that is our complex functions. And this complex function, q over s, is so special. And here, from the beginning, when we introduce a complex function like this function can be any value of s. For whatever the s we plug in, then we can calculate corresponding values, the magnitude and phase angle. For this example, we have to find the particular values for s to make this equation satisfied. So, for example, here, say if I give you a k value, how can you find the S. Okay. For this one, we are given a value of S. We find the information about this. So you can see the two things are kind of reverse process. That be right? Okay, so again, for this one, it's kind of straightforward. We plug in the value of S for whatever the S, we do the calculation. For this one, we are given this information, we need to find the value of S. Basically, find the value of S, there's many possible values for S. And collection of those S simply give us is a root loci. Okay, so right now I gradually kind of guide you through the whole things and then back to our focus for making a root loci here. Okay, so keep this in mind. So in this way, again, for this one, if we want to find the value of S satisfying those things, then probably we can try is again, we can start from the relation between the magnitude and the relation between the phase angles on the both sides. We see what happened. Again, we still take up the two rules, the phase angle and the magnitude. Okay, so here, to satisfy these equations, we must have this. Again, the magnitude on the both sides must be equal. Okay, so here, so for example here, let me add one more line here. So say, okay, so here in this way we are given the value of k, we're going to find S. So in this way, that means we have to guarantee the magnitudes on the both sides must be equal. So which means here, QS and LES should be equal to, that's the magnitude on the left-hand side, equal to the magnitude on the right-hand side. The magnitude on the right-hand side basically is this. This is a complex plane, real, the major part. And say k is non-negative, so for example, that should be -1 over k should be certain negative real number, so that should be here, okay? So that is a point here, so the magnitude simply is the distance from here to here, right? So here is the magnitude of this, and actually is 1 over k, right? Okay. The second one, we're asking the phase angle on the two sides must be the same. And what is the phase angle between, what is the phase angle of a negative number here? So if you look at that one, the phase angle basically is measured from, right now the point is here. If you're using the vectors, and that is this. So this is the phase angle here. Okay, so phase angle basically is equal to pi. If you remember, the complex plane is a multiple values and multiple values. So basically this is a pi, and that's equivalent to this one, mod pi, right? So basically here can be equal to 2 pi. If you have one more loop, and that will be the same. So basically that is 2n pi, and n equal to 0, 1, 2, etc. Okay, so here we have a multiple possible values for the same. And again, if you like, and for this case, if you wish, you can say, for example, say, let me say if this is 30 degrees, then we can say this phase angle of this one, whatever is 30 degrees, and you can also say this is plus 2 pi, 390 degrees, and or etc. Okay. So basically that is have the same in the mode of 2 pi. Can I change a symbols? can I change this one back to L because I like to make it consistent with whatever I get used to be. Okay, so anyhow, this is just a symbol here. So, so those are if we are given, again, if we given the K, if we want to find the value of the S, then basically we have to satisfy the two equations. And all the value of the S satisfying the two equations at the same time, those S will be determined as the poles, the roots of these equations. Again, this is the standard form of the characteristic equations. And here again, I try to build up integrate the concept of the complex functions to our looking for the roots of the characteristic equations. So again, this is the standard form of the characteristic equations. Okay. So for finding this one, so basically, again, if you're going to solve for this equation, basically you are going to solve for this. So which means given K and solve for 1 plus K QS PS equal to 0. So that means solve for the root of 1 plus K QS PS equal to 0. Okay. And the root of this one basically is the poles of the system. Okay. So this side basically is the foundations of these chapters. And again, to draw the root locus, and actually is asking us to solve for the two equations, to solve for us that satisfy the two equations at the same time. And how to do it, and we might go to the traditional, the complex function techniques, but those one won't give us too much insight into the geometry of the root locus. And in control, people develop a few rules, and 6 or 7 depends on the versions of the textbook. And by completing those rules one by one, we will be able to solve for the roots. We will be able to solve for these questions precisely. Okay. So again, these will be our foundations for these chapters. And so based upon this, let me get more derivations.